Unlocking the secrets of quantum gravity, a new frontier in physics. Imagine a world where the fundamental laws of physics are pushed to their limits, and the fabric of space and time is manipulated in ways that defy our current understanding. This is the realm of quantum mechanics and gravity, two theories that have been known to be incompatible, yet are essential to understanding the universe. But here's where it gets fascinating. What if we could merge these two theories and create a new way of exploring the interplay between quantum mechanics and curved spacetime? This is exactly what scientists have achieved in a recent breakthrough, demonstrating that quantum networks of clocks can be used to investigate how spacetime curvature influences quantum mechanics. Quantum networking is rapidly advancing across the globe, with the promise of building a worldwide quantum internet that would allow for secure communication on a massive scale and enable the linking of quantum computers over vast distances. Efforts to turn this vision into reality are already underway, both on the ground and in orbit. However, in a recent collaborative study, researchers have discovered that quantum networks may have capabilities beyond secure communication. Led by Igor Pekovsky from Stevens Institute of Technology, along with Jacob Covey at the University of Illinois at Urbana-Champaign and Johannes Beauregard at Harvard University, the study has opened up a new scientific possibility. The findings, published in PRX Quantum, reveal that quantum networks can be used to investigate how spacetime curvature influences quantum mechanics. This marks the first experimental approach of its kind, and it's a game changer. While quantum theory has consistently stood up to experimental testing, its behavior in the presence of gravity remains uncertain. Einstein's theory of general relativity redefined gravity not as a force, but as a result of the bending of space and time, a concept known as curved spacetime. This curvature gives rise to unusual effects, such as the slowing of time near massive objects like planets. But how does this changing flow of time affect quantum mechanics? Could quantum theory or general relativity, or both, require modification where they intertwine? These are the questions that have puzzled physicists for decades, and now, thanks to this new study, we may finally have a way to explore them. The researchers have shown that superpositions of atomic clocks in quantum networks would pick up different time flows in superposition, and that this opens the door to probe how quantum theory and curved spacetime intertwine. According to Igor Pekovsky, the interplay between quantum theory and gravity is one of the most challenging problems in physics today, but also fascinating. Quantum networks will help us test this interplay for the first time in actual experiments. By teaming up with Covey's lab, Pekovsky and Beauregard developed a concrete protocol that exploits modern quantum capabilities, such as quantum teleportation and entangled bell pairs in atom arrays. This protocol allows for a test of quantum theory on curved spacetime, which is a major breakthrough. And this is the part most people miss: the implications of this study go far beyond the realm of quantum mechanics and gravity. It challenges our current understanding of the universe and forces us to rethink the role of quantum networks. As Pekovsky puts it, we assume that quantum theory holds everywhere, but we really don't know if this is true. It might be that gravity changes how quantum mechanics works. In fact, some theories suggest such modifications, and quantum technology will be able to test that. The results of this study demonstrate that quantum networks are not only a useful practical tool for a future quantum internet, but that they also provide unique opportunities for the study of fundamental physics that cannot be achieved with classical sensing. At the very least, a test of how quantum mechanics behaves on curved spacetime is now possible. But here's the controversy: what if the results of this study challenge our current understanding of quantum mechanics and gravity? What if they reveal that our current theories are incomplete or even incorrect? These are the questions that spark debate and encourage discussion. So, we ask you, what are your thoughts on this groundbreaking study? Do you think that quantum networks will revolutionize our understanding of the universe, or are there still too many uncertainties? Share your opinions in the comments below and let's start a conversation. The future of physics is being written, and we want to hear from you. Never miss a breakthrough. Join the SCI Tech Daily newsletter and stay up to date with the latest developments in science and technology. This new experiment could take us closer to a theory of everything. Imagine a world where the mysteries of the universe are finally unraveled, where the rules of the smallest particles align perfectly with the grand tapestry of space and time. This tantalizing vision of a theory of everything is closer than ever before, thanks to a groundbreaking new experiment published in PRX Quantum. 3 visionary scientists in the United States have designed an experiment that could bridge the gap between quantum mechanics and Einstein's general theory of relativity, 2 pillars of modern physics that stubbornly refuse to work together. While quantum mechanics explains the behavior of subatomic particles, general relativity describes the universe on a cosmic scale, dealing with the intricate dance of space, time, and gravity. Despite their individual successes, these 2 theories have never been able to reconcile their differences. Dr. Igor Pekovsky, an assistant professor of physics at Stevens Institute of Technology, New Jersey, explains the challenge. Both quantum theory and Einstein's theory of gravity are well tested and work exceptionally well, but combining them into a single theory remains the most important challenge in modern physics. Something just doesn't click, and no joint theory has succeeded so far. Pekovsky, along with Dr. Jacob Covey from the University of Illinois Urbana-Champaign and Dr. Johannes Beauregard at Harvard University, has devised an experiment that could finally reveal how these 2 seemingly incompatible theories might coexist. Their goal is to uncover how quantum effects respond to the influence of curved spacetime, a concept first introduced by Einstein. Curved spacetime is the fabric of the universe, warped by the mass and energy of celestial objects. According to Einstein, gravity is the result of this curvature, causing time to flow more slowly near massive objects and more quickly further away. The scientists' experiment involves a network of atomic clocks which can measure time with incredible precision. By entangling the quantum states of these clocks and allowing them to exist in multiple states simultaneously, they can experience different flows of time simultaneously. Placing these clocks in different locations within the quantum network allows the scientists to detect subtle differences in the flow of time caused by gravity's influence on spacetime. If performed, Pekovsky explains, such a test would be the first verification of a quantum theory on curved spacetime, demonstrating how quantum systems behave even when Einstein's gravity is taken into account. This experiment is a crucial first step towards testing the compatibility of these 2 theories, but it relies on existing technology. Pekovsky hopes that this research will inspire a new wave of interest and excitement about the many mysteries that nature still holds. There is still so much we don't know about the universe, he says, and this experiment opens the door to exploring some of these questions for the first time in real-world experiments. As we stand on the cusp of this groundbreaking discovery, one can't help but wonder, what secrets will the universe reveal when we finally unlock the power of a theory of everything? Will the laws of quantum mechanics and general relativity coexist in harmony, or will we discover an entirely new framework that defies our current understanding? The debate is just beginning, and we want to hear your thoughts. What do you think about this experiment? Could it be the key to unlocking the ultimate secrets of the universe? Share your thoughts in the comments below. Revolution in physics, quantum wave disturbs spacetime, redefining gravity. Goodbye to gravity as we know it, quantum wave makes spacetime tremble. For over a century, physicists have wrestled with a contradiction at the heart of modern science. While quantum mechanics governs the microscopic world with uncertainty and superposition, gravity has stubbornly remained a force described by classical physics. The dream of uniting these 2 frameworks, often called quantum gravity, has hovered as one of science's ultimate goals. What's at stake is more than theory. Without evidence that gravitational attraction behaves quantum, the disconnect limits how far we can push technology and hinders our understanding of the universe's earliest moments. Gravity's impact on the universe. Black holes, the Big Bang, and even spacetime itself remain partly out of reach as long as gravity resists quantization. The pressure to close this gap is mounting, and researchers are chasing ways to probe the force that holds the cosmos together. Now, for the first time, physicists have designed an experiment that could expose gravity's quantum side, not by peering into deep space, but inside a laboratory at MIT. Researchers from Aalto University have developed a new theoretical model that tries to describe gravity using quantum mechanics. Their approach aims to fit the force within the standard model of particle physics, something scientists have been chasing for decades. If this framework holds up, it could help explain some of the biggest mysteries about how the universe began. The work was published in Reports on Progress in Physics. This new theory can change gravitational studies. Physicists have long worked toward building a unified theory that connects gravitation with the other fundamental forces, electromagnetism and the strong and weak nuclear forces. The difficulty lies in combining two frameworks that don't naturally fit together: quantum field theory, which describes particles and forces at very small scales, and Einstein's theory of gravity, which explains how massive objects like planets and stars interact. Interestingly, even technologies like smartphone GPS depend on Einstein's model of gravitation force to work correctly. In the study, researchers Mikko Partanen and Jukka Tulkki explain how they used a type of mathematical structure called a gauge theory to approach gravitation. Gauge theories already describe the other fundamental forces, like electromagnetism, so applying similar ideas to it could be a step toward treating all four forces within one consistent framework. Instead of following the traditional spacetime-based approach of general relativity, their model uses symmetries similar to those found in the Standard Model. This shift could help overcome one of the key challenges in modern physics, finding a way to describe both the smallest particles and the largest cosmic structures. https://www.ecoportal.net/universe-mystery-strange-structures/94997, using a single theory. Current models work well in their own domains: quantum physics for the tiny, and general relativity for the massive. The difficulty in studying gravitational forces. One of the reasons gravitation is so hard to study at the quantum level is that it's an incredibly weak force compared to the others. Measuring its effects in particle-scale experiments requires much higher precision than typical setups can handle. But in extreme environments, like near black holes or during the first moments after the Big Bang, the gravitational force and quantum effects both play key roles, and physicists need a theory that accounts for both at once. According to the researchers, their method uses renormalization, a mathematical tool that helps handle problematic infinities in calculations. So far, they've shown that the method works for some basic cases, but they are still working to prove it can handle more complex scenarios consistently.